Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last 2-3 classes, I was talking about organosulfur chemistry. I talk about the discovery of the sulfurs and then the different type of organosulfur compounds, and then I talk about the elite chemistry. In the today's class, my plan is to talk about some of the other important reaction. I think also if you remember in the last class I also talked about sulfur based different reagent for oxidation of alcohol to aldehyde or ketone. You have seen different type of name reaction which was developed by activated DMSO, okay, based reagent, and also we talk about some other variations. But I missed the one of the important reaction is the Swan oxidation. So in the today's class I am going to start with the Swan oxidation and then talk about the Pumera rearrangement, very important reaction using sulfur, Mislo-Evans, some other 2-3 sigmatopic rearrangement reaction, okay, and then I will end up with using the Chagaev elimination. Okay. I think if you remember in the last class I talked about there are several different variations of this particular reaction where what you are doing, you are converting alcohol to corresponding aldehyde or ketone. Okay, so the idea is we are using DMSO, dimethyl sulfoxide. I think you have seen in the several slides I talk about this, and always I talk about if you try to do a resonance structure, because of the electronegativity difference of the sulfur and oxygen, you can see there is a huge difference in electronegativity. So you will always you can think about this as a the electron density is actually on the oxygen. So you can think about S plus and O minus. Okay. So now you can see by using different type of other other reagent, we have seen using acetic anhydride, using several other things we have talked about SO3 pyridine, you have seen oxidation happening, correct, from alcohol to aldehyde or ketone. In Swan actually developed first initially in 1976, Professor D. Swan and co-worker reported the oxidation of primary secondary alcohol using DMSO and trifluoroacetic anhydride. You can see it's a very similar to the Goldman oxidation which I have discovered in the previous class, okay, where you have seen that was a DMSO and acetic anhydride, correct. So what Swan group developed, they replaced acetic anhydride with trifluoroacetic anhydride. That was the original discovery. Later in 1978, they modified their condition using oxyl chloride instead of trifluoroacetic anhydride. So what they are doing, they are trying to change this, because if you remember at the beginning, in this particular reaction which I talked in the last class, that this this O minus is attacking here to this acetic anhydride to get to the O acetyl. If you remember that, then it, this will come back and this will break. That means you are somehow trying to make this activated sulfur, correct. Once you make that, now then the you have the alcohol which is going to attack here, and then there will be a formation of some sort of elite type things, and then there will be proton abstraction, formation of the double bond, correct. But then what happened after that discovery, what they find out that this one, the using oxyl chloride becoming really better, this reaction is very clean, and this reaction is if you have a sensitive group, it is only stopping at aldehyde, it is not going to the corresponding acid. So they found that if you use oxyl chloride and DMSO, and then you have to use a base here, it is very important, because once you understand you are using oxyl chloride, one of the important thing using oxyl chloride that you will be getting some sort of a Cl minus, correct. So that is going to take H from the alcohol to make HCl. So now you need a base to quench the acid which is forming in the reaction. So now, so this is kind of a beginning to the Swan oxidation reaction. Again, I think the one at the beginning, the earlier discovery using trifluoroacetic anhydride, here the mechanism is again the O minus is attacking, as I mentioned here, cleaving of this bond. So you know the anhydrides, these bonds are weaker, you form these activated species. Now alcohol attacks there, one alcohol attacks there, you can form this product. It's very similar to all the previous oxidation, and then you can see here this proton will be taken by this oxygen going to form this species. Now this can allow you to, in case of base triethylamine, allow to form generation of this type of ylide species. And once that is happening, this this CH2 minus can take this proton from this alpha proton to this corresponding alcohol to form this carbon oxygen double bond to convert to the corresponding aldehyde or ketone. In case of oxyl chloride, you can see mechanistically now this is a this will be a more reactive one compared to the trifluoroacid anhydride. So this will react even at minus 78 degrees Celsius. This reaction can happen to get to this. So now you are actually forming another intermediate. It is not if you remember, it is kind of mimicking the other oxidation you have heard, which is they used NCS, correct, using N-chloro succinamide, if you remember. So Core group actually developed the oxidation where they are also forming this species there. Again you can see this is sulfonium with a chloride there. This is a very reactive, so the alcohol going to attack the sulfur, okay, and then you can now this proton will be so again you can see here there will be a HCl going to form because the Cl minus going to take this H plus here, so that will be quenched by triethylamine. And now then again now the mechanism will be very similar. You have seen in the previous case also, it will be forming this ylide CH2 minus. This can take this proton from the double bond, get to the corresponding product, and dimethyl sulfide is the your byproduct. Again you can see the one of the important step which I didn't mention might be is this. So this is a very important step. Why I am saying that, what is your byproduct? Look into it. Here you are not generating anything. This is all are volatile stuff which is getting out from your reaction. So your reaction byproduct is CO2 and CO and dimethyl sulfide, all are volatile. So that is the importance of this reaction. The reactions are very clean. You are not generating a byproduct which you have to kind of separate out from the reaction. It is getting out from the reaction because these are gaseous compounds. So this reaction again used there are several applications. If you see, if you are in organic synthesis lab, someone must be using Swan oxidation for their synthesis. So excellent yield was achieved in Swan oxidation for these particular transformations here. You can see again minus 70 degrees Celsius, triethylamine as a base, and you have this alcohol here. So what we are seeing here, you have a allylic alcohol one side and you have a primary alcohol, both of them getting oxidized, okay. But if you do this reaction using a Jones oxidation or the PCC oxidation, they are, first of all, in case of PCC, in case of Jones oxidation there will be over oxidation happening, and in case of the PCC oxidation the yield was poor, okay. Some more example here, you can see there are some sensitive functional groups in this molecule. There is a tertiary alcohol here, there is a primary alcohol here, and again by Swan oxidation you can selectively oxidize this. Again this is a tertiary, so the primary alcohol is only getting oxidized. But not only that, now you can see here this is the linkage here, correct. So you can see this is have a some sort of a ketal linkage here, so that these are also getting not getting decomposed. The product getting isolated in a good yield, which is finally converted after a few steps to an important natural product. So you will see that Swan oxidation was used for several natural product synthesis, where you will see there are some sensitive functional groups. The other important the reaction using or the rearrangement using the sulfur chemistry is the Pumera rearrangement. So we learn about sulfoxide. Now we are going to learn that by starting from sulfoxide, if you can use a proper activating agent and of course the solvent and then acid or base, what you are going to form? You are going to form a alpha substituted compounds, alpha substituted sulfides. So from sulfoxide you are synthesizing alpha substituted sulfides through a rearrangement called Pumera rearrangement. It was discovered in 1909. Okay. So acidic anhydride is the most widely used activating agents, okay, for this reaction. So most time you will see acidic anhydride is the one used for this reaction, but these are the other activating agent can be also used, like the acid, different type of acid, different type of Lewis acid or different other combinations, all can be used for this rearrangement. Sometimes co-catalysts are used to minimize the side reaction, okay. So if there is a, you are going to see there are some sort of side reaction, to stop them sometimes you can use the co-catalyst. And once you form this, again if you are using acidic anhydride, then you end up forming this nucleophile will be a O-acetyl. So if you go for if acidic hydrolysis, then you end up forming a carbonyl compound and a thiol, because you can clearly see if you have something like a OAC, then this can get out from the sulfur, can put the nucleophile, then if you have a H3O plus, then the water can attack, then this carbon sulfur bond will be clipped, that will form the thiol and the corresponding carbonyl compound. You can see the mechanism of the Pumera rearrangement. So as I said, the DMSO, so again the sulfur is plus, oxygen minus is attacking to the acetic anhydride. You guys have seen that in case of previous cases where you use this as an oxidizing agent for the alcohol. So here what is happening, first once it is attacking the OAC minus, so this part is coming out to form this this particular compound. Now the OAC minus can take this proton, form this carbon sulfur double bond. Okay, so you can talk about this type of compound as some sort of a thiol compounds. So if you have that, you can try to draw a resonance structure. Now you can understand that any type of nucleophile will be attacking in this particular carbon. Okay, so that can end up forming this particular product. Okay, so you can see nucleophile can be trapped in this type of activated thiol species which is forming in this reaction. So by using an activating agent, what you are doing, you are kind of generating this type of species here in the reaction, where the nucleophile can be attacked and form this product. Again, the intermediate is so electrophilic that even the neutral nucleophile can be also used. Means you can think about some sort of a fiddle cup type of reactivity here. That means what they are saying, that this particular thiol species which is forming here also, you see this oxygen will get out at the end. So what you end up forming a double bond here. So this type of species are really, you can see this is also attaching with the electron withdrawing group. These are very reactive. So that's why you can see if you use some sort of a electron, like a electron, you have a electron rich system here, then they can participate in a fiddle cup reaction to get to this type of product. Okay. So I talked about in the previous slide where you have seen that you have a nucleophile coming into the picture and you have the sulfoxide. Here I am talking about a intramolecular version. Again, there are different type of nucleophile can be here. There is a list of nucleophile I have given here. Could be alcohol, acid, and of course the O-aryl means again O is oxygen electron rich. So you are seeing again the sulfur, nitrogen, they can be also nucleophile. So here I am talking about intramolecular version. So now you have this sulfoxide here, and you have olefin there, like some sort of a styrene. This is not a normal olefin. This is styrene. So once you use a PTSA, what is going to happen? They can protonate this styrene to generate a tertiary carbocation here, which is also a benzylic. Now that can allow this, you can think about that the sulfoxide as a sulfur plus O minus, this can attack to the corresponding carbon. Okay, and then it can from here you can see after formation of that this proton can be abstracted to form this type of thiol species here, where the oxygen of this. So now once this bond is getting cleaved, you are generating a OH. Now the oxygen lone pair can attack the thiol in this position here to neutralize the charge to generate the alpha acyl oxy thioethers. So starting from this simple sulfoxide, you are generating a alpha acyl oxy thioethers. Again, there are several synthetic applications here. I am just trying to show you some of them here. Now you can see this SO2pH, this SOPH, which is the corresponding the sulfoxide using acetic anhydride and sodium acetate. You see some cases you have to use sodium acetate. What it is doing, it is going to convert this, and then once you put water, it is going to convert them to this species here, which can at the end get rid of this alcohol. So you can think about now this can come back, so it and then get rid of this part. Sorry, it is going to get rid of this part to get to the corresponding aldehyde. So you have seen it's a first activation, and then you have a nucleophile which is going to attack. You have the water as a nucleophile which is attacking here, getting rid of that species, going to the corresponding carbon compound. Okay, so from sulfoxide you are getting this sulfoxide eliminated, and this carbon getting oxidized to the corresponding aldehyde, which can be converted to the very important compound. Here there is another example here. You can see you have this, the sulfoxide here. Now you are using TMS triplet. So again the TMS triplet, if you remember, TMS triplet can activate the oxygen here, the O minus can be from the OTMS here, and once you have OTMS, once you use a TBAF here, so once you use TBAF, this is going to form a O minus, it is going to come back and get rid of the SPH, so it is going to form the corresponding thiophenol, and this going to convert to the corresponding aldehyde. Okay. So you can clearly see that in these cases, this is the oxygen which was there in the corresponding sulfoxide, which actually coming to the corresponding aldehyde. So the aldehyde oxygen is coming from there. Okay. But here in the previous case, if you seen there, this is the water actually which is going to getting attacked. So the water alcohol, or the water, sorry, the water in the OH group, actually finally you can see that in the aldehyde oxygen. Okay. So the oxygen from the water is actually transferring to the water of the aldehyde. I am going to talk about the Mislo-Evans rearrangement reaction here. So this is a thermal rearrangement of allylic sulfoxide. I am talking about allylic sulfoxide to allylic alcohol. So if you have a allylic sulfoxide and you want to convert to corresponding allylic alcohol, then you can use this Mislo-Evans rearrangement. It was discovered by 1966 by Kurt Mislo, and then in later the Evans group has have done some further development. So this reaction is a 2,3 sigma-topic rearrangement. So you can, if you see here, I am going to go to the mechanism in a minute, but before that, what you are going to learn here, what is happening from here to here all the way. First thing, we can use base and R2X. So if you have a base and R2X, you can clearly understand these are the protons which are acidic, going to form a carbon ion. Then you are going to, there will be SN2 to form this R2. Correct. So that can go for SN2 to form this carbon-carbon bond. Now once you have a thiophile and workup, so this is the step where you are going to see this 2,3 sigma-topic rearrangement going to happen to get to the corresponding product. Again R1 could be alkyl, aryl, and R2 could be again alkyl, aryl, or properzyl, or even benzyl. And in case of base, you can use butyl lithium or LDA, okay, for this reaction, and there are several different thiophiles which can be used. So thiophile means this is a nucleophile which is going to take the sulfur. So let's try to understand the mechanism of this reaction. What is, so this, as I mentioned, there is a 2,3 sigma-topic shift happening here. So after the formation of this this bond, now what is happening? You have to put heat. Again, you can think about the sulfoxide is a sulfur plus, oxygen minus, so this O minus. So you can think about this as a 1, 2, and this can be a 1, 2, 3. So this can tell you this is a 2,3 sigma-topic shift. So the O minus is attacking here in this position, and this double bond is pushing here, breaking this carbon sulfur bond to get to this type of intermediate here. From there it is going to form this compound. Now you have to use a thiophile. It could be a phosphorus, it could be a nitrogen which is going to attack to the sulfur, cleave the sulfur oxygen bond to form this corresponding compound, corresponding allylic alcohol after the protonation. Okay. Again, there is a synthetic application here. So again, as I mentioned, that from corresponding disulfide, if you use a MCPVA, it is going to convert to the corresponding sulfoxide. Now you have this allylic sulfoxide here, and once you look into allylic sulfoxide, you should doubt that if you see some sort of a phosphorus or nitrogen based reagent, you should always think about that there is a 2,3 sigma-topic shift happening. Okay, here what is happening, again you can think about a sulfur as a plus, this is a minus, so this can come and go for a 2,3 sigma-topic shift, and there will be cleavage of the carbon sulfur bond, and then once you have this SO, then once you have that compound where you will have you have a methyl here, OH, and you will have a again you can understand that once this the stereochemistry here is kind of getting shifted here. So in this rearrangement you end up generating a OS pH. Okay. And then what is going to happen? Then you are using this diethylamine. So Et2NH. So that amine in lone pair can attack on the sulfur, leave this bond, and then that O minus will be taking proton to get to the corresponding product. Okay. So there are several other variation of this. Again, you can see this is a, as I mentioned, in this particular variation, what you are seeing, you have some sort of a azasulfonium, in a salt, some sort of azasulfonium species here. So this azasulfonium species, once you have done, once you have the phenol can react here in the sulfur to cleave this sulfur nitrogen bond to form the oxasulfonium salt. Once you have a oxasulfonium salt, in place of base, these are the proton going to be abstracted to form the corresponding carbon ion here. Now this carbon ion can able to attack here. Okay, you can see very similar to some sort of a like smiles type rearrangement here, though this can attack here through a 2,3 sigma topic rearrangement, then going to form the double bond oxygen, form this intermediate, this proton will be abstracted to form the get back to the corresponding phenol, and now you have this CH2S CH3, so you have the disulfide in the ortho position of the phenol. So after the nickel, if you do a Raney nickel reduction, then this carbon sulfur bond will be cleaved, it will generate the corresponding ortho methyl phenol. Okay. Several other variations of this type of reaction. Now as I mentioned in the previous slide that you are starting from this azasulfonium salt and then you are making the oxasulfonium. But you can start from this azasulfonium salt in case of aniline. If you have aniline, then it can react with that. If you have some sort of a species like SCl, then that can be, you have a like a leaving group here, plus then that can be attacked by corresponding aniline to form this. It will form the azasulfonium. Now again, if you have this base in the medium, these protons will be the acidic proton going to be abstracted, form this type of elite, and now it can participate in this 2,3 sigma topic rearrangement, form this intermediate. Now this proton will be getting abstracted to form a aniline, and then you have this the tetrahydrothiophene, which if you use a nickel hydrogen, then these bonds will be cleaved, which will end up giving you the butyl group in the ortho position. So you will get a ortho-butyl aniline. Okay. So this is a very interesting way to introduce substitution in the ortho position of phenol and the aniline. Another example here, so this is a very interesting example because here you end up making, starting from this azasulfonium salt, you end up making a very important compound called indole, and not only that, you are introducing, so if you see indole has this 2 and 3 position, you are forming a 2-methyl indole. Okay. So sometime if you can see, instead of the Fischer indole synthesis, this method will be comparatively better. You can able to form this azasulfonium salt from the corresponding aniline, and now if you have a triethylamine in the medium, then it can able to form this corresponding elite by abstracting this proton. And once you have a elite, and you can see these are this can take part in the 2,3 sigma topic rearrangement to attacking here, formation of the carbon nitrogen double bond, cleavage of the nitrogen sulfur bond to form this intermediate. Again, if you know that this proton will be abstracted to form a double bond here, and a NH, finally it will take a proton to form NH2. And now you can see you have a amine and you have a carbonyl group. So they will condense to form a imine, and that can able to finally this proton will be going to form a NH here, and you can see, now you can clearly see you have a SME group at the C3 position and C2 position having a methyl group. Now once you treat with the Raney nickel and hydrogens, this is going to cleave the carbon sulfur bond to form the 2-methyl indoles. Okay. So in this part, I think I'm going to finish in this part introducing a very important elimination reaction, which is called the Chagaev elimination. So this is a formation of a olefin by pyrolysis. Okay. So I talk about this in the before also, that if you have a xanthate which you are forming, then if you are heating the corresponding xanthate, then it can participate in a scene elimination. So this is called a Chagaev elimination, okay, which was discovered in 1899. Again, you start with a alcohols, 1 degree, 2 degree or 3rd degree alcohol. You use a base to deprotonate the alcohol, treat with carbon disulfide to form, and then you use the corresponding alkyl halide to get the corresponding alkyl xanthate. And once you have a alkyl xanthate, once you heat up the alkyl xanthate, it is going to form this corresponding olefin. So again, this is a scene elimination happening, and we are going to come back to the mechanism in a minute. So the xanthates are prepared from the corresponding alcohol by treating them with a base with carbon disulfide and alkyl iodide. Okay. Primary xanthates are usually more thermally stable compared to the secondary and tertiary. As you can see that in case of secondary, tertiary, the reaction is happening faster compared to the primary. Again, it is a very important reaction for conversion of sensitive alcohol to the corresponding olefin without rearrangement of the carbon skeleton. Okay. So let's try to learn the mechanism. First, as I mentioned, you kind of forming this alkyl xanthate. This mechanism is very easy. You are deprotonating the alcohol, attacking to this carbon disulfide. Then again there will be SN2 reaction to form this corresponding alkyl xanthate. Now once you heat up the xanthate, what is going to happen again? The sulfur, sulfur are nucleophilic. This can able to take this proton, form the double bond, and it will form the carbon oxygen double bond. So that is a driving force here. You are cleaving a carbon oxygen single bond to form a carbon oxygen double bond at the end. Okay. And you can see it can we have shown here it is goes through some sort of a tangent state here, where the H and the corresponding xanthate will be on the same side. They will go for a scene elimination. That's why if you see the there will be a steric interaction here. To avoid that, you have to heat the reaction at the high temperature, so that this will be feasible to get to the corresponding product through the scene elimination. Again, this has used for for several natural product synthesis. One of the example here. So in this synthesis, they want to get rid of this corresponding alcohol, primary alcohol, to form this olefin, and that was converted to the corresponding natural product. So now I think that again the sodium hydride and carbon disulfide. Again, sodium hydride will be selectively forming the O minus, that will treat with carbon disulfide. Then if you treat with methyl iodide, that will go for SN2 to form the corresponding xanthate. And now you have to just heat up the reaction with over 200 degrees Celsius. Once you do that, this reaction will be clean and formation of the corresponding olefin here. And then again there is another example here. In this particular reaction, you will see this is a here this is a secondary alcohol. Potassium terbutoxide is used, and to abstract this proton, then react with carbon disulfide, methyl iodide, to get to this xanthate. Now you have to you are treating with 190 degrees Celsius. If you treat with 190 degrees Celsius, you can see there is a this is the proton, which is again xanthates are sterically bulked, so it will try to find a proton which are kind of having a less steric. And also, as you see, this is a scene elimination, so that's why this proton is actually not in the same side. This is in the opposite side, so that's why it is going to take the proton which are in the same side. So you can think about there will be two proton, one is like this, one is like this. So it is going to take this proton which are in the same side and form the corresponding olefin here. And now if you use the lithium aluminum hydride, if you remember, lithium aluminum hydride can convert the corresponding ester to the corresponding alcohol, and after that you can able to get to the corresponding natural product. So in this particular part, I talk about the sworn oxidation, and then the very important the Pumera rearrangement, and you have seen Mislow Evans, this 2,3 sigma tropic shift. and again I end up in talking about the chuggable elimination. Again, these are the textbooks. Again, the Claydon books is very good if you try to follow this chemistry. Again, thank you so much for coming to the class, and I'm going to see you guys in the next class. Thank you.